Before we get into today's topic, let's quickly recap what we learned about the history and evolution of artificial intelligence in medicine. Artificial intelligence as a field began in 1956. In the 1970s, early systems like MYCIN showed that computers could help diagnose infections using rule-based logic. Fast forward to today, artificial intelligence is everywhere in healthcare, from radiology and dermatology to critical care with tools like sepsis prediction systems. The key lesson is this: artificial intelligence has always been designed to assist, not replace. Doctors remain at the center of decision making. Now, let's move into the basics, the core technologies that power artificial intelligence in medicine. Machine learning, or ML. This is when artificial intelligence learns patterns from large data sets, instead of being programmed step by step. For example, if you train it with 100,000 ECGs, it can predict the next one. Deep learning, or DL, a specialized branch of machine learning that uses layered neural networks loosely modeled after the human brain. Deep learning is especially powerful in image recognition, making it ideal for radiology, pathology, and dermatology, and natural language processing, or NLP. This allows artificial intelligence to understand and interpret human language. In medicine, it can extract key details from messy clinical notes or even transform a doctor-patient conversation into structured, usable data. These aren't just theories. Artificial intelligence is already being used in hospitals today. In radiology, Phu General Hospital in Vietnam deployed a system called VINDAR CXR. It automatically analyzes chest x-rays and highlights potential abnormalities for radiologists. In a study of more than 6,000 scans, it proved effective in real-time clinical workflow. In critical care, a multi-hospital study across 9 medical centers showed that an artificial intelligence algorithm for early sepsis prediction reduced mortality, shortened hospital stays, and lowered readmission rates. And in dermatology, convolutional neural networks are now being tested in clinics to classify skin lesions. Some of these systems can detect melanoma with accuracy comparable to dermatologists, offering faster triage and decision support. These examples show how artificial intelligence is not replacing clinicians, but actively supporting them, making care safer, faster, and more precise. So, to close this section, in Part 3 of Module 1, we introduced the basic technologies behind artificial intelligence in medicine and saw how they are already shaping clinical practice. In Module 2, we will take the next step, looking at data, algorithms, and medical applications. This will give us the foundation for understanding how artificial intelligence actually works in practice and why the quality of data is just as important as the technology itself.